Welcome back. Today, in this session, we're going to talk about Bootstrap. We are going to continue the discussion we started about cross-validation and work on another resampling method called the Bootstrap. In my opinion, the Bootstrap is one of the most genius techniques have been introduced to statisticians. It has been introduced by Professor Bradley Efron in 1979 and a very wonderful paper that was published. And it's a method by which you can pretty much estimate the standard error of your estimators or parameters that are being estimated, or build up confidence intervals for any estimation method that you use. And that's a very powerful technique. As I said, it can be applied anywhere, and the idea behind it is just genius. I cannot stress enough on the importance and the beauty underlying this process. So the bootstraps are very flexible, are powerful, and they use to estimate the standard error of the coefficients that are being estimated or build up the confidence intervals. The idea behind the bootstrap comes from the from story where a baron were stick at the bottom of a deep lake. He wanted to help himself, and he found there is nothing else he can do, but he used his own bootstraps to get out of the lake. So the idea is here the bootstrap idea is the same. We do not know what the population is. We are sticking to the sample we have. We use that in a way to help us to build up resamples from it and build up the confidence intervals or standard errors we want from our data. And the idea is somehow different from the boot that we have in computer science. So the term comes from actually this story that I just shared with you. So let's work on an example. This is a financial example. Let's say you have a very limited source of money. You just want to spend it on two assets or two stocks. These two stocks are X and Y, so you want to spend alpha percent or alpha portion of your money on stock X, and the rest, which is 1 minus alpha, on the stock Y. So basically, we want to divide whatever we have into two portions, alpha and 1 minus alpha. We want to spend 1 minus alpha on Y and alpha on X. Usually in finance, we are interested in minimizing the risk. So the total money we spend is alpha X plus 1 minus alpha Y. Risk in mathematics is variance. So we are trying to minimize this risk by choosing an appropriate alpha. So we're minimizing it over alpha, and we want to take this variance a bit. Okay, so alpha was the portion that we wanted, so we want to choose the portion that is correct. So the alpha we are going to choose should be between 0 and 1. It can be shown that mathematically the correct alpha is a portion that is not only related to the variance of Y and variance of X, but also covariance of XY. So let's see what it says. So let's say you're working with an asset like Y, which is extremely risky. Let's say sigma 2y goes to infinity. That's a very risky asset. If you're using this asset, so you will have infinity on numerator and infinity in denominator. So and since we only have 1 degree infinity, the ratio is 1. The limit of that will be 1. So alpha will become 1. So let's see what alpha equal to 1 means. Alpha equal to 1 means we spend all of our money on X. If our goal is to minimize our risk, why should we spend anything on Y? And that's exactly what this ratio is giving us. And that's the same for X. Let's assume instead of sigma Y, variance of Y, variance of X is converging to infinity. If that's the case, we have a small number here, we have infinity in top and bottom. So if you divide this ratio, you get 0. That means if you're having such a risky asset like sigma 2x here, like X here, you're not going to spend anything on X, but you are going to spend everything on Y because alpha will become 0. Now let's look at another case. Let's say sigma xy is 0. So we have two uncorrelated assets. And let's say sigma 2x and sigma 2y are just the same. So we have equally risky outcomes. It's easy to show that if you just plug in numbers here, you will see alpha will become 1/2. So it's very natural that if you have some two neutral equally risky assets, you're going to spend half of it on x and half of it on y. So basically what this equation shows is that for different values of x's and y's, how we will spend our money, how will we divide the portion of the asset we have and spend it on different stocks. So if we have the real underlying variance of y, covariance of xy, and variance of x, we can find the actual or correct alpha that we want to spend. But unfortunately, we only have a sample of it. Since we do not know what tomorrow will happen, that hasn't happened yet, we do not know the population. Since we do not know the population, we only know a subset of it, and that's why we can only estimate the variance of y, covariance of xy, and variance of x. That's the only thing we can do, and therefore we can only estimate alpha hat. Let's say I tell you alpha hat is equal to half. So you may get into notion to say, okay, since alpha hat is equal to half, I am going to spend half of my money on x, half of my money on y. But let me add one thing to it and say, okay, with 95% confidence, alpha hat belongs to somewhere between, let's say, 0 and 1. Then you would tell me that this estimate is not reliable at all. How do I know it's 0 or 1? If I would flip the coin, I would get a better estimate. But let's say you knew that with 95% confidence, alpha hat belongs to, let's say, 0.49 and 0.51. They would be you would say, okay, that's a very reliable estimate, and I would spend half of my money on x and half of my money on y. But how can we find these confidence intervals or standard errors that we're looking after just in this very sophisticated ratio? In some of the cases like this, unfortunately or fortunately, I say why I said fortunately. Unfortunately, we do not have closed form solutions for standard errors. Why did I say fortunately? I said fortunately because of this problem, a wonderful technique like Bootstrap has been created. So now let's see what this Bootstrap is. So before getting there, I reiterate what I said earlier. Alpha hat is just, we cannot know alpha because we do not know population. We just have a sample of it, so we basically estimate it. So now our goal is to find the standard error of it. So now let's assume you had access to God. So God would create 100 samples for you, and these 100 samples will be this. So the first 100 sample God created to you would look like this. So you look at these 100 samples, you have different x's and y's. And let's say these are the percentage of time x and so for example here corresponds to an observation where x improved 0.75% and y got negative 1% return on it. So as you can see, there is some correlation between x and y, some positive correlation. Usually when x went down, y went down, and when x went up, y went up. So you just estimate sigma 2 hat x, sigma 2 hat y, and sigma hat xy from this, and you just put it in the formula we had. You estimate alpha hat, and let me call it alpha hat 1, and you estimate it to be 0.576. You ask God to create another 100 observation for you, and this is this one. You do the same thing you did earlier, and you estimate the new alpha hat 2, and this one is 0.532. You ask God to create the third one, and this is here. You estimate alpha hat from it, and you get 0.657. And lastly, you ask God to create the last one from the population. It has access to all reality because he knows. So God has a role that he knows actual sigma 2x, actual sigma 2y, and actual sigma xy. So that's God. He knows that because he's God, or she's God, depending how you want to refer to God. So last time we create new 100 fresh samples for you, and you estimated alpha hat 4 as 0.651. So you can ask God to create samples over and over and over again, and each time you get alpha hat 1. Then you put different alphas you have, different alphas you create, and you get histograms of what you have. So basically, let's say God was playing with these numbers. So the random generating machine that God had has variance of x equal to 1, variance of y 1.25, and covariance 0.5. And if you plug these numbers in, since these are realities, the real alpha would be 0.6. So that's what God did. And he created thousands of samples. Each one had 100 observations inside. Okay, so 1,000 samples. In previous slide, I showed you 4 samples. So let's say he created 1,000 of samples. Each sample had 100 numbers, and you get alpha. You estimated alpha hat 1, 2, alpha hat 1,000. So if you do that over and over and over again, and estimate the mean and get the average of all alpha hats. So for example, it will be alpha hat 1 up to alpha hat 1,000 divided by 1,000. The number you get is very, very close to actual 0.6 that is reality. This was real alpha. This is the average of alphas you got. And you can also estimate the standard errors that are there. It's very easy to find the standard errors. That's just a standard deviation. So it will be deviation squared summed up divided by n minus 1 squared. So this is the standard error of this estimate, 0.053. And if you just put it on a scatter plot, you get something like this, and this is histogram. So this part, so for a second, just disregard this blue curve. And this yellow histogram, we see how many times out of those 1,000 times of simulation we get different. For example, around 250 times or 300 times, alpha was estimated between 0.55 and 0.6. Around 230 times, alpha was estimated between 0.6 and 0.65. And remember, real alpha was 0.6. So this is the histogram of all alphas that could be estimated. If God would create samples of size 100 and does it 1,000 times, that's the real distribution of outcomes we would get based on the formulas we got. And this is the scatter plot of what we have. This is the scatter plot. This yellow one is the scatter plot. Sorry, not the scatter plot. Sorry, box plot. The box plot of this histogram. It shows that this it has some pretty symmetric shape. It is scattered around 0.6. 0.6 is reality, and it did a pretty good job because it was reality actually. And this standard error we estimated to be I forgot what it was. Oh, the standard error was 0.083. But unfortunately, not everybody has the privilege to contact God directly. So not everybody can contact God. So we only usually have 100 observations that we have to rely on. We only have 100 observations. And that's a one-time thing. So that's the sample we have. We don't have thousands of these samples. We only have one sample, and that is it. So the idea behind, and based on that sample, you can only get one estimate, and this is alpha hat 1. Oh. Based on this sample, I don't know what happened. Okay. Based on this sample, we can only get one alpha, and let's call it alpha hat star. So we cannot get the standard error from it. We cannot do anything from it. The brilliant idea came from Bradley Irfan in 1979 was that, yes, we don't have got to create samples of size 100,000 times for us, but we have a sample of size 100 and we can resample from it. So the idea is, why don't we sample from this sample with replacement? I don't know what's going on here. Okay. So the novel idea behind it is that why don't we sample from these 100 observations with replacement? We can do it many ways. So let me call it observation 1, observation 2, up to observation 100. Let's sample from it 1,000 different ways with replacement, and that's the key. So in order to show you what it means, let's look at what it has. Let's assume we only have 3 observations, 1, 2, and 3. The first sample, if we sample 3 observations from it without replacement, you always get 1, 2, 3, because you don't have any other choice. But if you sample from it with replacement, you get some repetitive answer. For example, the first sample has 2 3s in it. So observation 3 happened here 2 times. The second sample had 1, 2, 3. The third sample has 2 2s in it, 1 1. So you can do it many different ways. And let's say we do it 1,000 times. Each time we sample from it, we estimate alpha hat star from it. Each time we do it, we estimate alpha hat star from it. And if we do it over and over again, we can get a histogram of all alpha hat stars, and that will be this blue curve. So this blue curve are the distribution of alphas have been estimated by resampling from this original data set we had with replacement. Each time we sampled 100 observations from it, 100 observations with replacement. For example, 100 here, the 100th observation had chance to be picked more than once in our 100 in those samples. And each time we sample from it, we just estimated the alphas for it. And if you do it over and over again, you get this histogram. First of all, as you can see, this histogram is very close to it. And if we just draw the box plot of it, we can see that box plot is actually very close to it. Specifically, this standard error is very much the same as the standard error you would get from the yellow one. So from the sample itself, by resampling from the sample itself over and over and over again with replacement, we were able to estimate the standard error of it, and that's the beauty of it. Although we didn't have access to Go, we just resampled from the same data set we had over and over and over again, and we get the histograms of alphas that we had. First of all, it's not necessarily normally distributed or symmetric. It can have any shape. And when you do that, you can easily find the standard error of alpha hat, and that is if you bootstrap from it b times, that will be 1 over b minus 1, summation of the differences of whatever you estimate from these alpha hat stars minus the average of all squared, for instance. Let's say in the first time I get alpha hat star 1, and in thousands times, let's fix b to 1,000. By the way, the more the better. You can just do it as many times as possible. The more the better. But let's say due to computational limitations we have, we only do it 1,000 times. So we did it 1,000 times, the average of all these 1,000 times is alpha hat star bar, and that's alpha hat star 1 up to alpha hat star 1,000 divided by 1,000. And by the way, here B is 1,000. This is the last one we had. So this is alpha hat star 1. So in order to find the standard error, you just subtract the first alpha hat from this mean, square it, add it up to the second alpha hat star minus this value squared, and so on and so forth. So you do it, you get the standard error, and the standard error you get from this Bootstrap is 0.87. Look how close it is to reality. If you were asking God to provide samples for you, you would get this estimate, 0.083. Now, when you did Bootstrap just from this very sample, you get it 0.087. So he did pretty darn good job. And that is why I said this was brilliant. The first time I was introduced to this concept, I was blown away, and I really admired the job that Bradley Afron did. And this is a schematic picture of what we're doing. In general, we want a random sample from the population. We do it over and over again to get the sense of the standard error of our estimates. Unfortunately, we do not have access to population, so we use the sample and resample from it over and over again with Bootstrap. And in the Bootstrap world, you resample from the original sample you have, and you treat that as your estimated population, and you build up the standard errors there. So that's pretty genius. So you can, if you work with cross-sectional data, meaning non-time series data or non-panel data, it's pretty much easy to use Bootstraps. But in more sophisticated version of it, when, for example, you deal with time series data, we should be careful to how to Bootstrap, because in time series data, you usually have a relationship like this. For example, YT, you want to see what is the relationship of it with T minus 1, what happened before, or for example, beta T minus 2. So we have autocorrelation most of the times. Or you can add some other variables here. So we have these autocorrelations here. So we have, it's important for us when we sample, we consider this relationship. So the observations we have are not independent anymore. So one of the ways to deal with that is to build up blocks. For example, let's say we have observations in first period, second period, third period, up to 1,000th period. And let's say we are pretty much sure if 3 observations are blocked together, these 3 observations would be, let's say, independent from the next 3, and so on and so forth. So if that's the case, then we do Bootstrap, but each time we Bootstrap, we pick a block here instead of just individual observations to adhere to that independency assumption. This is called block sample blocks. So we should be careful to deal with that. The Bootstrap works best when you have cross-sectional data. And the next concept we want to discuss is how do we build up the confidence intervals. So as I said, in more complex settings, for example, if you want to deal with confidence interval around median or certain percentiles, we no longer have normal distribution that we can rely on. For example, say 95% of data is within 2 standard deviation over standard. We cannot say that anymore. So, but fortunately, we have the empirical distribution of our outcome. And if we have that, if we want to build up, let's say, a 90% confidence interval, you can work on the 5th percentile, and 95th percentile, and just report that as your confidence interval. For example, here we had 1,000 observations, right? It's easy to say, for example, okay, by here, 25 observations have been observed, right? So our 2.5, and 25 out of 1,000 is 2.5%. So the 2.5 percentile is 0.4. And I think, yeah, if we just stick to here, we can say after that we have 25 observations. So we can say 97.5 percentile is 0.75. So we can say our 95% confidence interval is between 0.4 and 0.75. So we are 95%, with 95% chance, the real alpha, the real proportion that we have to spend, the optimal one, is between 0.4 and 0.75. How do I get this 2.5 and 97.5 for 95% confidence? It's easy. Let me explain it in perhaps the next slide. Okay, so here. So let's say you're interested to build up, let's say, X% confidence interval. Confidence. So do the following. Say alpha is equal to 1 minus X%. Then look at the percentile of alpha over 2 and 1 minus alpha 2. For instance, if you want to build up a 99% confidence interval, that will be your X. Then alpha will become 1%. Then look at 0.5 percentile, and 1 minus 0.5 is 99.5 percentile, and report these two numbers. That will be your 99% confidence interval. You can also run a hypothesis test here. Remember, for example, if you run it on simple regression lines, if you're interested to know whether 0 includes a 99% confidence interval to see whether your model is significant at significance level 1%, you can see whether the 99% confidence interval that you built this way contains 0. And that's how you do it. So the next slide says, so let me finish that part. So this is called the Bootstrap percentile confidence interval method, and that's the simplest method out there. So even for the methods you already know the closed-form solutions, like simple regression models, which we have complete confidence interval. We know that the error we can use t statistic to multiply by a standard error to get the confidence interval we want, or in logistic regression, when we use Fisher index matrices, Fisher information matrices, to the inverse of that to get the standard errors and confidence intervals, we can still use Bootstrap. So Bootstrap is so powerful, it doesn't matter how you use it, and you can show that the Bootstrap confidence intervals you make are actually almost identical to what you get from closed-form solutions that we have closed-form solutions, let alone those we do not know what the closed-form solutions are. During the homeworks, you will see you can apply Bootstrap method in many different parameters that before, without knowing Bootstrap, it's impossible to build up the confidence over the standard errors. For example, you can build up confidence over medians or say 10th percentiles. That's genius. Okay, so can we use Bootstrap to estimate prediction error like the k-fold cross-validation? No, we cannot. because Bootstrap resamples with replacement. So part of our test error, if we just divide our data into training and test set, part of our training error may have test inside it. So unfortunately, we cannot use Bootstrap to estimate prediction error. At the same time, we cannot use cross-validation. We cannot use cross-validation to estimate standard error of our parameters. So remember that do not try to use Bootstrap where you have to use cross-validation. Do not use cross-validation when you have to use Bootstrap. To summarize what we have discussed in the last two videos, chapter 5 of your textbook, cross-validation, which is sampling without replacement, which you divide your data into k different subgroups and use k-1 as training and the last partition as test set, and you do it over and over again to get the cross-validated error. Our goal is to first find the correct flexibility of the model, and second, to find the standard error of our predictions. At the same time, the Bootstrap, which is resampling with replacement, tries to find the standard error of your estimates, not your prediction, the parameters that are being estimated. So these two methods have two different applications. Do not mix the two. There's some people who try to mix the two and somehow use Bootstrap to find cross-validation, vice versa. I'm not a good fan of it, so I'm not suggesting that at all. My suggestion is, whenever you want to find the error, test error, and error of your predictions, use cross-validation. Whenever you want to use and find the error of your estimates, and you don't have any better way to do that, use Bootstraps. So we conclude the course here. We learned two resampling methods, cross-validation and Bootstrap. And later on, we are going to use these two methods in R. Thank you so much for watching.